Welcome! In the previous video, we have seen how the topic of this course is in ODEs and PDEs. Now I would like you to give some examples to prove why ODEs are that interesting. And the key thing that I want you to remember of this lecture is that we know physics because we know how things change over time. And the form in which the change over time comes to us is through an ODE. So if we can solve ODEs, we can understand a lot of physics. And in this specific case, I'd like to go through two examples. First of all, I'd like this video to be on the spring model. So how does a spring work? Well, the very simplified version that we will look at is that we have a wall on which there is attached a spring, and at the end of the spring we put a weight, something with weight m. If the spring is at rest, then we call the position of our mass 0. But if the spring is overstretched or understretched, then our mass will not be at position 0. So our position 0 is a bit further away. You understand that in this case, for example, the string is overstretched and it's going to try to push our mass back. We say that the position of the mass is x. And x will be depending over time. So what is the formula for x? Well, you can imagine that first of all, the law of motion will be very important, so I will remind you that F equals m times a, where a is the acceleration of x. So a, in this case, is x double prime t, so the second derivative of x. And then we wonder what is the force that we're going to push on x. And the force is very simple, because what we have is that the spring is just trying to get back to the position it had. And it's trying that with a constant force towards 0. So we have a force that goes in this direction that depends on k. And the further away you are from the position 0, the stronger is this force. The closer you are, the weaker it is, and it's linear. So this force is kx. The further you are away, the stronger it's pushing you back. But this is just the magnitude of it. What is the sign? Well, if x is to the right, kx is pushing to the left. So we also have to remember that there is a negative sign in here. So the force applied by the spring is really minus kx. So if there is no other force than the force on the spring, the full picture that we can get from this is that mx second equals minus kx. And we'll add a plus f of t. This is the idea that you can come in and mess with the experiment and add an additional external force in any direction. So here is the force of the spring, and this is an external force. So this is the equation for the spring. This model that we have drawn here, it's very useful in engineering. It's called a free body diagram. I'll write in white and not in red, so it's easier to read. So free body diagrams are extremely useful. And we're going to straight away use it in the second examples. The second example we will be dealing with is the pendulum model. The first thing we do is draw the free body diagram. So the pendulum, it's the idea that there is a wall at the top, and we're connected to the wall through one single point. I know the drawing shows that it's bigger, but it's really just one single point through which you have a straight rod attached to it and a mass attached to the bottom. Because the straight line is fixed, it's not going to change, how you can define the position of this thing is through the angle theta between the vertical and your rod. So we're going to try to describe how theta changes over time. The force that is applied on this mass is straightwards down the gravitational force, mg, where m is the mass of our pendulum itself. So how does this change? Well, the first thing you have to think about is that we're not interested in the straight downward force. We're only interested in the component of it that goes perpendicular to our rod, so that goes in this direction. Why is it? Because that is the only direction in which we can move in this moment. So our acceleration will have to be along this plane. So we need A to be in this direction. And in order to do that, we have to split our vertical force in two parts. The part that is along the direction in which we can move, and the part that is, so to say, wasted because it goes, that is just pulling on the wall and have no result. So if you do a little bit of trigonometry, what you have is that theta, the angle here, is also this angle here and this angle here. So this component here is mg times, this is theta as well, times sine of theta. So the force that is applied to our pendulum is mg sine of theta. What we have is that E is equal to F, and we know by the law of motion that F equals m times A. So the thing that happens here is that our two masses just disappear, and that means that the motion of the pendulum is independent on the mass itself. And we end up having A equal g times sine of theta. We remind ourselves that A is the acceleration, and in this case it's the acceleration of theta. So what we have is theta double prime equals g sin theta. And this is the equation of the pendulum. So these two examples were to show how it's very easy to derive equations of motion when you can use derivatives. So when we try to harness the power of ODEs, we do that because we want to be able to solve these problems.